Almost every powerful AI system today is trained to maximize a reward. A number that says, this output was good, that one was bad. But here is the uncomfortable truth at the heart of AI safety. We do not actually know how to write down a reward that captures what humans really want. So instead, we try to learn it from human feedback, from demonstrations, from comparisons. Which raises the deepest question of all. If a machine learns our reward, can we ever prove that it learned the right one? This video is built on a blog sequence by Joar Skalse, written near the end of his PhD at Oxford. It is called The Theoretical Foundations of Reward Learning. Instead of running experiments, Skalse asks for mathematical proofs, guarantees about when reward learning works, when it fails, and exactly why. We will walk through the sequence post by post, building up the whole theory from scratch. No prior background assumed, just curiosity. Let's start with the first post, which lays out the whole research agenda. Skalse splits AI alignment into two halves. Outer alignment is the problem of writing down the right goal. Inner alignment is the problem of getting the system to actually pursue that goal. This research is squarely about the outer half. The dream is a complete mathematical theory of outer alignment. The agenda is organized around a chain of questions. What language should we use to express goals to an AI? Reward functions or something else? How close must two goals be before one can be safely swapped for the other? How do we even measure the distance between two reward functions? Does a given learning method converge to a good reward? And how sensitive is it to wrong assumptions? Answer these, and you can finally say which reward learning methods are trustworthy. But why focus on reward functions at all in the age of large language models? Skalse gives a sharp answer. Reward maximization is the only method that is not anchored to what humans already know how to do. Think of chess. You can train an AI by imitating human games, but then it can never clearly surpass humans. To invent genuinely new strategies, you must let it optimize a goal of its own. So sooner or later, we will hand a powerful AI a reward function and say, go. We had better understand what happens next. Much of the sequence zooms in on one method in particular. Inverse reinforcement learning, or IRL. Normal reinforcement learning goes from a reward to behavior. IRL runs that backwards. It watches behavior and tries to infer the hidden reward behind it. It is the only reward learning method that is self-supervised, so we have oceans of data for it. If IRL could be made to work, it would be a huge deal. The whole question is, can it? This brings us to the second post on partial identifiability. It summarizes a paper with Matthew Farrugia-Roberts and Adam Gleave, and it confronts a fundamental obstacle. When you learn a reward from data, the answer is almost never unique. Many different reward functions fit the same data perfectly, even with infinite data. The reward is only partially identifiable. Here is the intuition. Suppose two reward functions always have the same best behavior. Then no amount of watching that behavior will ever let you tell them apart. The data simply does not contain the information. Skalse's move is to stop fighting this and instead measure it precisely. For each kind of data, he asks, exactly which reward functions get lumped together. He calls that set the invariance partition, the fingerprint of the ambiguity. The grouping turns out to be beautifully structured. Two rewards land in the same group when they differ by specific transformations that never change behavior. The first is potential shaping. You add a credit to each state and subtract it back later, so the totals are untouched. The second is S-prime redistribution, which shuffles reward between outcomes that have the same average. Both leave every optimal policy exactly the same. These transformations become the alphabet of the whole theory. Now the payoff. The paper works out the exact ambiguity for each kind of training data. If you only see the optimal policy, the reward is pinned down up to any optimality-preserving transformation. Loosest case. If you see a noisy, Boltzmann rational policy, you actually learn more, only up to potential shaping and S-prime redistribution. And RLHF, learning from noisy comparisons between trajectories, is tighter still. Each data source gets a precise signature. There is a genuinely surprising twist here. A noisy policy tells you more about the reward than a perfect, optimal one. How can adding noise add information? Because the noise is not random junk. Boltzmann rational agent makes better actions more often and worse actions less often, so the precise pattern of its mistakes leaks the underlying reward values. The noise is informative. The headline of the post is reassuring. For most data sources, the ambiguity is small, enough to recover the full ranking of policies. But that reassuring result hides a giant assumption. It assumes we know exactly how behavior relates to preferences. The third post tears that assumption down. It summarizes a paper that won the Best Paper Award at AAAI 2023. The key object is the behavioral model. The rulebook and IRL algorithm assumes for how a person's preferences turn into actions. In reality, that rulebook is always at least a little wrong. Here is the problem in one breath. Real humans are not perfectly rational. They're not even perfectly Boltzmann rational. So any behavioral model we write down is misspecified. It does not match the real process. The central question becomes, how robust is IRL to that mismatch? If a roughly right model gives a roughly right reward, IRL is feasible. If a tiny error in the model can produce a wildly wrong reward, we should give up. To answer this rigorously, Skalse needs a definition of being close enough. He uses equivalence relations. Two rewards count as the same if they share the same optimal policies, or, more strictly, the same full ranking of all policies. Then a behavioral model is robust to a misspecification if, despite the wrong assumptions, it still converges to a reward in the same equivalence class as the truth. A clever lemma lets him characterize this completely by composing transformations that preserve the relation. The results are a mix of good and bad news. The good news: Boltzmann rational model is surprisingly forgiving. Feed it data from a slightly different agent, and it often still recovers the right optimal policies. The bad news is brutal. No standard model is robust to even the tiniest error in the discount factor, or in the assumed dynamics of the environment. Get those slightly wrong, and the inferred reward can break completely. Notice that everything so far has been black and white. Same equivalence class or not. But we really want to say a reward is a little wrong, or a lot wrong. For that, we need a ruler, a way to measure the distance between two reward functions. The fourth post introduces exactly that. A family of metrics called STARC. Your first instinct might be to just subtract the two reward functions and measure the gap. The L2 distance. But that fails badly. Two rewards can be numerically miles apart, yet produce the exact same behavior. Because, remember, potential shaping changes the numbers without changing anything that matters. And two rewards can be numerically almost identical, yet induce opposite preferences. A good ruler has to ignore differences that do not matter and amplify the ones that do. So what should a good ruler actually guarantee? Skalse names two properties. A metric is sound if a small distance guarantees low regret. That is, if two rewards are close, then optimizing one instead of the other can only cost you a little. A metric is complete if the reverse also holds. Low regret guarantees a small distance. Together, sound and complete mean the distance is small if, and only if the two rewards lead to similar outcomes. Exactly what we want. STARC builds such a ruler in 3 clean steps. First, canonicalize. Strip away all the meaningless differences, the potential shaping, and the redistribution, by mapping each reward to a single standard representative of its class. Second, normalize, so that scaling a reward up or down does not fool you. Third, measure the ordinary distance between the two standardized rewards. Standardize, then compare. That is the whole idea. And then comes the elegant theorem. Every STARC metric is both sound and complete. Its distance is 0 exactly when two rewards share the same ranking of policies. Even better, any two rulers that are both sound and complete are essentially the same, up to a constant stretch. In other words, STARC is not just one way to measure rewards. It is up to rescaling, the canonical way. You cannot do meaningfully better. Armed with this ruler, the fifth post returns to the misspecification question, now in full color instead of black and white. The paper is quantifying the sensitivity of IRL to misspecification. Before, we could only ask, is the reward exactly right or not? Now we can ask, how wrong does the reward get as a continuous quantity when the model is slightly off? The central concept is perturbation robustness. If the observed behavior is nudged slightly, does the inferred reward only move slightly? Skalse proves this holds if, and only if the behavioral model is separating. Separating means rewards that are far apart always get mapped to behaviors that are far apart. If two very different rewards can produce nearly identical behavior, you are doomed. You will never tell them apart from the data. And here lands the hammer. Skalse proves that no continuous behavioral model is separating. None. There will always be two rewards that are far apart in the STARC sense, yet produce behavior so similar that any smooth model blurs them together. Combined with the earlier discount factor result, the verdict is bleak. A tiny, unavoidable error in our assumptions can produce a large error in the learned reward. Skalse's own conclusion is striking. He would not currently put much hope on IRL. The sixth post turns from learning rewards to optimizing them. It summarizes a paper with Nikolaus Howe, Dmitry Krashenikov, and David Kruger on reward hacking. We almost never have the true reward. We have a proxy, an imperfect stand-in. Reward hacking is when an AI pushes the proxy up, while the thing we actually care about goes down. Question: can we design a proxy that is provably impossible to hack? First, a crisp definition. A proxy is unhackable if there is no way to increase the proxy while decreasing the true reward. Hope was that we might build simplified proxies, rewards that ignore some details of human values but are still safe to maximize. A bit like how a simpler function can preserve the direction of a more complex one. If that were possible, alignment would get a lot easier. We would not have to encode every last thing humans care about. The answer is a hard no. The paper proves that the only unhackable proxies are the trivial ones that ignore everything, or the ones that are already equivalent to the true reward, sharing its exact ranking of policies. There is no middle ground. No genuinely simplified, genuinely safe proxy exists. This is a rigorous justification for an old fear. To avoid Goodhart's law, your proxy must be essentially identical to what you truly want. The seventh post steps back and connects the dots to a wider web of results. How expressive are reward functions, really? There are tasks like press this button a finite number of times that no Markovian reward can express, but other languages can. When does Goodhart's law turn catastrophic rather than merely annoying? Each thread reinforces the same lesson. The choice of how we specify goals has deep, often hidden, consequences. The final post is a toolbox for newcomers, and it hides a genuinely beautiful idea worth pausing on. The occupancy measure. For any policy, you can write down how often it visits each situation. That vector is its occupancy measure. And here is the magic. The value of a policy is simply the dot product of its occupancy measure with the reward. That makes value linear in the reward. Suddenly, hard questions about rewards turn into clean problems in geometry. This single trick powers many of the proofs in the whole sequence. The post then lays out shovel-ready open problems for anyone who wants to contribute. Extend all these results from simple environments to partially observable and multi-agent ones. Find even better rulers for comparing rewards. Work out how to optimize a known-to-be imperfect reward conservatively and safely. And compare reward functions against rival specification languages. Skalse stresses that this field is unusually tractable. The proofs are within reach. So step back and take in the whole arc. Reward learning is partially ambiguous, but the ambiguity is usually manageable. IRL is dangerously sensitive to small errors in our assumptions, especially about time and dynamics. We finally have a principled, near-unique ruler for comparing rewards. And there is no free lunch on proxies. To dodge reward hacking, your proxy must basically be the truth. Piece by piece, this is what a mathematical theory of outer alignment looks like. Skalse argues this agenda is both crucial and tractable. With a bit more attention, he thinks a real mathematical theory of outer alignment is achievable within a few years. If that excites you, the full sequence is on the alignment forum and less wrong, and the open problems are waiting. All of the work in this video is his and his co-authors. We have only tried to make it easier to enter. Thanks for watching, and go read the originals.